Rates of reaction, also known as chemical kinetics, which includes not only how fast reactions go, but also the pathway that a reaction takes. Kinetics is based on collision theory. Collision theory states molecules must collide to react with each other, and not all collisions are effective. Each collision must have sufficient energy, that is, enough energy to break the bonds on the reactant side of the equation. Consider this hypothetical chemical reaction pictured. We have atom A colliding with a diatomic molecule that contains one atom of B and one atom of C. During the collision, the bond between B and C must break. So, slow collisions that don't have enough energy to break that bond will not be effective. Also, we're forming a bond between A and B. So, collisions where atom A doesn't hit atom B perfectly, like say atom A collides with this molecule on atom C. Well, that won't be effective because it can't form the bond between atom A and atom B. Let's take a look at the simulation. So here I have a molecule of BC, and here is atom A, and I can launch it into this box and have it collide and do some reactions. So let's see what happens. So you can see bonds are breaking and forming at the same time if the collision is perfect. But now look, the collision has gotten off track. We're no longer linear. Now we've got rotational motion. And you can imagine that the more complicated the molecules are, the harder it is to have favorable orientation. So we had reaction happening pretty fast in both the forward and the reverse direction. Now, the reaction's happening much slower. How could I speed it up? Well, according to collision theory, anything that increases the rate of those collisions is going to increase my reaction rate. So what if I add some heat? Got my little simulated fire here. You can see now my molecules are going much faster, and it's really hard to keep track of what's happening. I'm hoping we'll get a reaction here. There it was! We had a reaction, holy cow. And another reaction. Spectacular! So a corollary to collision theory is that we can increase the rate of reaction by increasing the frequency and or the force of the collisions. So how could we increase the rate of collisions? Well, you saw one way, by raising the temperature. That means all of the molecules travel faster because you're raising the kinetic energy. And the faster the molecules are going, the more often they will collide with each other. Another thing we could do is raising the concentration. The more molecules there are in the container, the higher the concentration is, the more likely they are to collide with each other. Let's go back to the simulation. So I'm going to pump one pump of A molecules in there, or A atoms. That puts 3 atoms in. We'll do the same thing with the BC atoms. So we've got 3 of each. Now you can see our rate of reaction is not particularly fast. So, what if I add more of each? So now I have doubled the concentration, but you can see not a single reaction event has taken place yet. This is because I have increased the concentration, so the collisions are more frequent. But none of the collisions has enough energy to break bonds. Or very few. This is called a reaction coordinate diagram. And it shows this is the energy of the reactants, this is the energy of the products, and this is the energy barrier we have to get over. It's called the activation energy. That's how much energy is required to break the bonds. So, let's increase the temperature and see what happens. Now my molecules are moving a lot faster, and look, I've got some reaction happening. Now if I wanted to drive this reaction backwards, I could put in more product molecules. So let's put in some AB molecules, and let's put in some C atoms. And now it's a free-for-all. Now my rate of reaction is happening pretty fast.